following conditions. And the conditions are that f prime of x, or f prime of x is always negative. And f double prime of x is also always negative. Okay, so questions like this are good because it requires that we look at the information, the clues about a function f's derivative and second derivative, and based on that information come up with an example of a picture that satisfies all of these requirements. And you know how much I like to ask for, give an example of blah, blah, blah. Okay, so we had one with the limits on the last exam, and then an example of continuous but not differentiable, I think, and a few other examples like that. All right, so Andrew, you looked at this and you read it. What were your thoughts?
I was lost.
You were lost. Okay, so here we're trying to draw a picture of a function, so I'm going to start by putting some axes up on the board. I'm going to draw a picture of y equals f of x. Now, here's the information we're given. We're given that the first derivative, f prime, is always negative. Now, when I see that, when f prime is negative, what does that tell us about the original function f?
Decreasing.
Okay, so when f prime is negative, that tells us that the original function f has a negative slope, or we can say that the original function f is decreasing. So I know that the picture of the function that I'm going to draw here is going to be a function that's going to start high and work its way down. So based on just that information, all I know is that this is the direction that my function is going to go. Now f double prime always being negative, what that tells me is that information tells me when f double prime is negative, that tells me that f prime is decreasing. And when f prime is decreasing, that means that my slopes on my original function are decreasing, meaning, okay, so maybe if we start here at a very steep slope, decreasing means that my slopes are slowly going to 0 and then slowly going negative. And so when f double prime is negative, f prime is decreasing and f is concave down. Okay, so what we need here is a picture of a function f that is going downhill, decreasing, and f must also be concave down. So not only are we starting high and going low, but I also have a curvature sense here. And so I could draw maybe something that looks like this. So my function f is decreasing, and this entire curve is concave down. So that's one example of a function f that satisfies these two requirements. Are there any questions about drawing that picture? Andrew, does that work for you?
That does, thank you.
Great. Jeff?
So I was kind of interpreting f prime being negative as, I think I asked you this in your office just a while ago, that the tangent slope would always be decreasing, but it is, but it's, at one point there, if it was increasing on the left side of where it starts.
Okay, so let me back up with your very
right.
first statement. You said, I was interpreting f prime being negative.
Well, you know the triangle?
Right. So that was the f double prime negative.
Right.
Corresponds to f concave down.
Right.
And both of those correspond to f prime decreasing. And so when I'm looking here, so maybe in the second one, if f double prime is negative, then that's when we think about the slopes as decreasing. Now, if my picture looks like this is a picture of a function f that is concave down.
Right.
But at the beginning of the picture, up until, let's call this point here, I don't know, C.
Mm-hmm.
Okay. So from A to C, f prime, so from A over to C, f prime is positive, f double prime is negative.
Right. And the question I asked you in your office
Yes.
was that when you say f prime is decreasing there, every tangent that it is on that curve
Yes.
is having the slope is decreasing.
That's right. So each tangent line that I draw, the slope of that tangent line is less than
The previous.
the slope of the previous tangent
Right.
line.
So when I was reading that problem, I was thinking, I was a little confused by what f prime is always negative meant, I guess, is all.
So f prime always being negative just means that if I were to draw a picture of y equals f prime, the graph of y
Right.
equals f prime is always below the x-axis. Now, whether this f prime is going uphill or going downhill, the fact that f prime is negative doesn't tell me any of that part. So, yeah, the only thing
Okay.
that f prime being negative can tell us is whether our original function is going uphill or downhill. There's no sort of shape going on with that.
Yeah, okay.
Okay, other questions about number 15? Okay, so let's take a look at number 35. So number 35, we have the function f of x is equal to x squared over x squared minus 1. And there are several parts to this one. Part A is to find the vertical asymptotes and the horizontal asymptotes. Part B is to find the intervals of increase or decrease. Part C, find the local maximums and minimum values. And part D, find the intervals of concavity and inflection points. And part E is to use all this info to sketch our function y equals f of x. Wow, so there's a lot of stuff that goes into this problem. Okay, so Erin, before we start this one, what are your thoughts?
Well, I went in order. I found the vertical asymptotes and then I found the intervals of increase or decrease. And then I think I know what I did wrong at C, but that's where I got to.
Okay, so you got up to C. So let's kind of go relatively quickly through A and B. So part A, finding the vertical asymptotes and horizontal asymptotes. For our vertical asymptotes, well, we are looking for places where our denominator is equal to 0, but where the numerator is not also equal to 0. If we had a 0 over 0, we'd have a hole in the graph rather than necessarily a vertical asymptote. And so in this case, our denominator is x squared minus 1. And so if we look at that and set that equal to 0, we can solve for x. And we get x is plus or minus 1. And those x values do not make the numerator equal to 0, so we're definitely talking about vertical asymptotes here. So these are our vertical asymptotes, x equals plus and minus 1. For the horizontal asymptote, to figure out what happens to our function as x gets really big and as x gets very small. To find the horizontal asymptote, what we're calculating is the limit as x goes to infinity of x squared over x squared minus 1. And so to work on this calculation, the long route is divide the top and the bottom by 1 over x squared and do the algebra to finish this out. But what we figured out when we were working with these infinite limits is that we can look at the largest power in the top and the bottom and focus on the coefficients in front of those values. So in this case, our largest power is squared on the top and the bottom. And so the coefficients in front are both 1s. And so our limit as x approaches infinity of x squared over x squared minus 1 is 1. And so that tells us that our horizontal asymptote is y equals 1. Okay, any questions about the horizontal or vertical asymptotes? Okay. So we'll need that information. Second part is to find the intervals of increase and decrease. So that means that we're going to be looking at f prime and figuring out where f prime is positive and where f prime is negative. So we have our original function f of x, which is x squared over x squared minus 1. And we would like to figure out where the derivative of this function is equal to 0. That's going to be the first thing. We want to figure out our critical numbers. So we'll take our derivative, f prime of x. And when I take my derivative, I'm going to have to use the quotient rule on this thing. So we have low, x squared minus 1, d high, 2x, minus high, x squared, d low, 2x. Draw the line and square below. Okay, so when we take our derivative, this is fine for the derivative, but we're eventually going to set this derivative equal to 0. And so we want to start by simplifying our numerator a little bit and cleaning this thing up. So this is where simplifying comes into play. So we've got 2x cubed minus 2x minus 2x cubed all over x squared minus 1 squared. Yes?
Before you do that, wouldn't you be able to get the x squared minus 1 out of the way?
This one here and here?
Yeah. Wouldn't that be easier?
I have to be a little bit careful. I cannot cancel this one because I've got addition or subtraction here.
Yeah.
But in addition to that, what I want to avoid also is that when we find our critical numbers, we want to include places where the derivative does not exist. So if I do that sort of a canceling, where I'm essentially canceling out a whole, then I might lose a place where my derivative does not exist. So I don't want to cancel those if possible. Okay, so now we've expanded this out, and now we can cancel the 2x cubes, and it leaves us with f prime of x is equal to negative 2x over x squared minus 1 squared. Okay, so in terms of critical numbers occur when f prime equals 0 or when f prime does not exist. So places where f prime equals 0, well, we have to set our derivative equal to 0. So we have 0 is equal to negative 2x over x squared minus 1 squared. We need to solve this for x. So solving this equation for x, I have a fraction, so my number one job here is going to be to get rid of that denominator, so I can multiply both sides by x squared minus 1 squared. On the right side, my denominator will cancel with the x squared minus 1 squared. On the left side, we're multiplying by 0, so I still have 0 on the left. And so I've got 0 is equal to negative 2x. And now to get x by itself, divide by negative 2. And we've got that x is equal to 0. so when x is equal to 0, our original function has a flat spot. Okay. This is one of our critical numbers. Now, the other possibility of having a critical number, and we didn't have to worry about this when all we had were polynomials, but now that we have a rational function, we have to think about, okay, when might f prime not exist? And f prime will not exist when the denominator is equal to 0. That's really the biggest issue. And so f prime does not exist when x squared minus 1 quantity squared is equal to 0. In other words, when our denominator is equal to 0. So to solve this equation for x, I could do some math that would make life harder. I could expand this out and then look at it and try and figure out what x is equal to. But to make my life easier, which is generally what I want to do, I can first of all take the square root of both sides. So I've got x squared minus 1 equals 0. And then when I move the 1 over to the right side, I've got x squared is equal to 1. Now remember, up here when I took the square root, I did remember the plus or minus, but it's plus or minus 0, so that's just 0. But down here, my x value must be plus or minus 1. Okay, so I now have 3 values which are considered critical numbers. Now, these two numbers down here, the x equals plus or minus 1, I'm going to put a little asterisk on those two critical numbers. The reason that I'm going to put an asterisk on those two critical numbers is that these two critical numbers are not actually x values in the domain of our original function. So technically, they're not really critical numbers, but they are important because they are places where our f prime value does not exist. Okay, so we want to take them into consideration. So we have 3 values that are important to us. X equals plus and minus 1 and x equals 0. All right, are there any questions so far about what's going on? We have not quite answered part B yet, but we're on our way. Okay? So our next step then is to create a table for ourselves. We're looking at intervals that are broken up by plus and minus 1 and 0. So my table will look like negative infinity up to negative 1, negative 1 up to 0, 0 to 1, and 1 off to infinity. And so on each of these intervals, I want to ask myself, first of all, what test value will I choose? And then I want to ask myself, once I plug that test value in, what will my value be for f prime of x when I plug that test value into f prime of x? Okay, so Erin, you said that you had come up with some values for this. So will you tell us what you used for your test values?
I used negative 2, negative 0.5, 0.5, and 2.
Okay, so these are all very reasonable values. And when you plug negative 2 into your derivative function, into f prime of x, what did you get as your output?
Positive.
Okay, so plugged in negative 2 and f prime became positive. Okay, and what about for the rest of these?
Positive, negative, negative.
Okay, so plugged in each of these x values, and our f prime values came out to be positive, positive, and negative, negative. Okay, so now what we want to ask ourselves is, what does this first derivative, what does the sign of the first derivative tell us about the original function f? The sign of f prime tells us when f is increasing or decreasing. So our result for f, when f prime is positive, f is increasing, going uphill. So f increasing over our first two intervals, and then f is decreasing over our second two intervals. Okay, any questions about this table that we've created here? Okay, so we are now ready to answer part B, find the intervals of increase/decrease. And so f is increasing on the interval from -infinity up to -1, and then from -1 up to 0. Is that right? Yeah, okay. And then f is decreasing on the interval from 0 to 1, and then from 1 to infinity. So that takes care of part B. All right, part C says to find the local maximum and minimum values. And local maxes and local minimums occur at critical numbers, and they occur when f prime changes from positive to negative or negative to positive. And so in this case, when I'm looking at f changes from increasing to decreasing right at x equals 1. And so our f prime is going from positive to negative. F goes from increasing to decreasing. That's our local maximum. And that's the
Isn't
0
it
one.
changing it to 0?
What did I say?
1.
Yeah, this is 0 right here. Thank you. Thank you. So at x equals 0. So part C, f has a local maximum at x is equal to 0. Now, part C says to find the local maximum and minimum values. When I see the word values, that means the y value. Okay? So our local maximum occurs at an x value of 0, and the maximum value, the local maximum value, is we have to plug 0 into our original function and get the y output value. So what was our original function? Our original function was f of x equals x squared over x squared minus 1. So f of 0 is 0 squared over 0 squared minus 1, which is -1. So that's kind of a bummer, because our local maximum is at a height of y equals -1. So we have a top of a hill at y equals -1. Occurs at x equals 0, the y value is -1. All right. Are there any questions about part C?
Just maybe how you got the -1.
This -1 right here?
Yeah.
So when I plugged in, so the local maximum occurs at x equal to 0. And I want to plug that into my original function to get the y value.
Got that.
And so when I do 0 divided by -1, I should get 0, right?
Yeah.
Yeah.
Yeah, so that should not be a -1 then.
Yeah.
Yeah, you're totally right. Yeah. Yeah, I'm trying to do my best to confuse you on this one.
Good.
Thank you.
All right, so we have 0 squared over 0 squared minus
Yeah.
1, which is 0
That's what I
divided
was-
by -1.
That's 0 there.
Awesome.
It's like-
Okay, 0 divided by -1 is 0. Thank you.
Okay. Woo.
Glad you guys are
There's something
good
major
to
there.
help me on that. Good.
Yeah.
All right. Other questions about
I know.
this one, now that we have that fixed? You guys don't assume that I know how to do arithmetic. You gotta help me out here. Okay, so this is part C. And the key on part C is find the local maximum and minimum values. If we were asking where the maximums and minimums were located, we would just need the x value. But because we're after the values, we need the y value as well. Okay, that's part C. Part D. Erin, you said that you got to part C and things went awry for you.
I got part C, but it was D, but I think I know what I did wrong. I just
Okay.
took the derivative of something weird instead of the derivative of, or the second derivative of the original function.
Okay, so should we keep going?
If
Yeah.
you want to.
Yeah, let's keep going. Let's finish this problem out. So this one encompasses a lot of information. So part D. First thing we need to do is to calculate f double prime. So I need to look back here and say what was f prime first of all. And f prime was negative 2x over x squared minus 1 quantity squared. So when I take this derivative, I have to use the quotient rule again. So I've got low x squared minus 1 squared d high negative 2 minus high d low. Yeah, so in my denominator, my derivative is going to involve the chain rule. So I've got derivative of the outside, keeping the inside the same. So that's 2 times x squared minus 1 raised to the first power times the derivative of the inside, so times 2x. So low d high minus high d low, draw the line, m square below. All right, so in terms of calculating the derivative, this is a fine derivative, but we are eventually going to want to set this equal to 0, so we should clean this up a little bit. So f double prime of x. First I'm going to FOIL out the x squared minus 1, so that will be x to the 4th minus 2x squared plus 1. And you can double check that by maybe expanding it out on the side. All of that times negative 2. And then over here, there's a lot of stuff to multiply together. I've got 2 negatives, so that will become plus. We've got 3 2's multiplied together, so that's 8. And I'll also multiply the x's, so we have 8x squared, and then times x squared minus 1. And in our denominator, we've got x squared minus 1 raised to the 4th. Okay, so I've combined a few of my like terms up here. And I still have a little bit more to do. For example, my negative 2 I need to distribute through my first set of parentheses. So we've got negative 2x to the 4th plus 4x squared minus 2. And over here, I'll distribute the 8x squared. We've got plus 8x to the 4th minus 8x squared. All divided by x squared minus 1 to the 4th. Okay, so we're not quite done simplifying in the numerator, but are there any questions so far on what we have? Going once. Twice. It's not pretty. Okay. Okay, so things that we can combine. We've got some x to the 4ths. So that's 6x to the 4th. We've got some x squared, so minus 4x squared. And then minus 2. Divided by x squared minus 1 to the 4th. Okay, so this is our second derivative. And what we want to work on is we want to ask ourselves, okay, when is this second derivative either undefined or when is the second derivative equal to 0? Jennifer?
8x to the fourth minus 8x squared?
8x to the fourth minus 2x to the fourth.
Oh, okay, okay.
Okay, so we want to look at this and say, okay, when is f double prime equal to 0? And possibly are there places where f double prime does not exist? And so f double prime does not exist when our denominator is equal to 0, and so that's when x is equal to plus or minus 1. So f double prime does not exist when x is equal to plus or minus 1. And f double prime is equal to 0 when, well, we have to set our second derivative equal to 0 and solve for x. So 0 is equal to 6x to the fourth minus 4x squared minus 2 over x squared minus 1 to the fourth. Alright, so setting this whole thing equal to 0, the first thing I can do is clear out that denominator. I can multiply both sides by the denominator, and it's going to knock that denominator out of the park. So I'm just going to knock it out of the park. And so we have 0 is equal to 6x to the fourth minus 4x squared minus 2. And this is a degree 4 polynomial that we are trying to factor. So when I look at this, one thing that I can do is, everything in here is divisible by 2, so let's knock these coefficients down by dividing everything by 2. So we have 0 is equal to 3x to the fourth minus 2x squared minus 1. So that makes the numbers at least a little bit better to work with. And the next thing that I might notice about this is, yes, this is a degree 4 polynomial, but it is quadratic-like in the sense that I have a x to the fourth and then half of that power in the middle and then a power of 0 over on the right side. So I can factor this kind of like I would factor a quadratic. I'm going to have a 3x squared and then an x squared is my other term. So that my first two terms multiply together to give me 3x to the fourth. And then I need two numbers that will multiply together to give me 1, which are going to be 1 and 1. And because this symbol is a negative, I know that I'm going to have a plus and a minus, and the question is, which order do they go in? Well, I need a negative 2x, so I'd better have a negative with the part that's going to multiply times a 3x squared. So you can double check this, but when we factor, my first term will be 3x to the fourth, my last term will be a negative 1, and my middle term will be x squared minus 3x squared gives me negative 2x squared. And so we end up with this as our factoring. Are there any questions on that factoring?
There's other ways.
What's that?
There's another way that you can do that, right?
Yeah? Like what?
Well, I'll just add the 1 on the 0 side. We factor out the x cubed.
So move the
So
1
move the
over
one over
to the
there.
other side?
But then factor out the x cubed. And solve for x for both.
And so then looking at x squared times 3x squared minus 2.
Right.
And then setting each of these equal to 1.
Yeah.
So what you have to be careful with here is that unlike the number 0, just because I have two things multiplied together doesn't mean that one of them has to be equal to 1. That trick or that technique only works when you have 0 on this side, because at this point here I can say either 3x squared plus 1 equals 0 or x squared minus 1 equals 0, but I can't do the same over here because these aren't necessarily, one of them isn't forced to be 1 over here. So I really do have to keep all my terms on one side and factor.
Would that be considered like a refactor?
What's that?
That's not the way to do it.
Yeah, so avoid doing this because If you move terms over to one side and then factor, you don't get this same technique, so avoid doing this. Okay, good, other questions? Okay, so now we've got ourselves 3x squared plus 1 equals 0, or x squared minus 1 equals 0. So if I look at this first one here, I subtract 1 from both sides, and I have 3x squared equals negative 1. And I'm kind of excited about this branch because I already see that I'm going to end up with an x squared. Oh, I don't want to erase this. But oh well, somebody will have to remind me what these asymptotes are. Okay, so 3x squared is equal to negative 1. Divide both sides by 3. And we have x squared equals negative 1/3. Which means when I take the square root, I'm going to have a negative under the square root. So there are no real solutions for this branch. So I don't have to worry about those two solutions. Now the x squared minus 1 equals 0. Well, that's the equivalent of looking at x squared equals 1, and so our x value is plus or minus 1. Mark?
So, I've been watching this, I'm trying to wonder, because we've said if the first derivative is positive, then the second derivative is positive too, so, right?
Not necessarily.
Because I thought you said it equals concave up. I've been trying to follow, what was the whole triangle?
So the triangle said when f double prime is positive, then f prime is increasing. And when f prime is increasing, then f is concave up. So it's not saying that, and so on this triangle, there's nothing in this triangle that tells me whether f prime is positive or negative, only whether f prime is going uphill or downhill. So we are actually getting new information by looking at the second derivative.
So as far as if f is increasing, it doesn't necessarily affect f double prime.
That's right, because you can have, here's an example of an f where f is increasing but concave down. So here, f prime is positive, f double prime is negative. Or you can have increasing but concave up. So now f prime is positive, but f double prime is also positive. So you can have either situation.
And then your intervals will change too quite often because they were the same, and I was kind of wondering.
So sometimes if these numbers line up, then we might have our function going from increasing to decreasing. In fact, you'll notice that this plus and minus 1 showed up a lot in this example. It showed up as vertical asymptotes. It also showed up in our f prime and our f double prime. So there's a lot of stuff going on at x equals plus and minus 1. Okay.
That's by design, probably just for this problem. Like as they get more complicated, those may not be in the same.
That's right. And when we looked at the polynomials, in fact, less complicated functions, we actually had different x values for f double prime than we had for f prime. It just so happens that here a lot of stuff is happening all in one place. Okay, so here we have our second derivative. We want to break up our x-axis into intervals and make another table for ourselves. And so here we've got negative infinity up to negative 1, negative 1 up to positive 1, and positive 1 up to infinity.
Don't include the square root.
So this one right here, these are not real values because it's the square root of a negative number.
Oh, right.
So you're right, if this had been a positive square root of 3, then yes, we would have to include these guys as well. But this led us down an imaginary world, or down an imaginary rabbit hole, so we don't have to worry about that one. Okay, so here we need to figure out some test values. So let's see, I'm going to go with a 0 for the middle test value. On the left, maybe a negative 2, and maybe a positive 2 on the right. And we're going to plug those into our second derivative function. Okay. Okay, so this was our second derivative function. And thinking about these numbers, I might crunch them in a calculator and say, okay, I'm going to plug in 0, and I'm going to plug in -2, and I'm going to plug in +2. I'm going to look at this and say, okay, no matter what, my denominator is always positive. Okay, no matter what we plug in, because whatever number we get, we're raising it to the 4th power. So our denominator is always positive. And our numerator, when x is equal to 0, we get 0, 0, -2. So we have negative over positive. So when we plug in 0, our f double prime is negative. And whether we plug in positive or -2 into this numerator, well, we're raising -2 to the 4th, and we're raising -2 to the 2nd. So these values are actually the same, whether we plug in positive or -2. And so I've got a really large positive number minus a medium positive number minus a tiny positive number. So you can double check this, but my numerator is going to be positive, whether I plug in positive or -2. Yeah?
So when finding concavity, can you plug in those test values into the original test values?
So if you plug those test values into the original f, then what you're doing is figuring out where the original function f is above and below the x-axis. Yeah. So we want to figure out where f double prime is above and below the x-axis. Okay, so this information here, f double prime, tells us about the concavity of f. So the result for the original function f is that when f double prime is positive, our original function is concave up. And so our middle interval, f is concave down. And in our last interval, f is again concave up. All right, so we now have our answer for part E. Is this part E or is this part D?
D.
Or part W?
D.
D. Okay, so our answers for part D are that f is concave up on the interval from -infinity up to -1 union -1 to positive infinity. F is concave down on the interval from -1 to 1. Okay, so those are our intervals of concavity. And inflection points occur when we switch from up to down or down to up. And so in this case, we're going to end up with inflection points at x is equal to -1 and x is equal to +1. Now, there's an asterisk on this. And the reason that there's an asterisk on this is, what is special about these 2 points in terms of our original function? Yeah, these are where the vertical asymptotes are on the original function. So these points are actually not part of our domain, which means that they really can't be inflection points. These are places where the concavity changes, but they're not going to be inflection points because they're not part of our domain. So instead of calling these inflection points, I'm going to say that concavity changes at these 2 points, but they are not inflection points since x equals plus or minus 1 are not in the domain of f.
So that doesn't get a special name for that?
for those points?
They're not inflection points, so it's just an explanation.
It's just an explanation, yeah. So just saying, our function's going to change concavity there, but because those x values are not part of the domain, they don't get a special name. They've already been kicked out. Okay, we now have nearly everything for this problem. Now we just need to sketch our graph. So let's do that, and then we'll take our 10-minute break. So I know that you're due for your 10-minute break now, but let's go ahead and finish this out, and then we'll take our break. Okay, so our last part is to sketch F. All right, so the information that we have a vertical asymptote, we have two vertical asymptotes. We have a vertical asymptote at x is equal to 1, and x is equal to negative. And we have a horizontal asymptote at y is equal to 1. Okay, so here is sort of the grid that we're going to be working with. Now, in terms of our function, f is increasing and decreasing on these intervals, increasing on the interval from negative infinity up to negative 1. So I'm going to draw a number line down here to help me with increasing versus decreasing. So f is increasing on our first interval from negative infinity up to negative 1, as well as from negative 1 up to 0. And then f is decreasing on the interval from 0 to 1 and from 1 to infinity. Okay, so we've got that information. We also have information about the second derivative. And our second derivative tells us that f is concave up on the interval from negative infinity up to negative 1, as well as from positive 1 off to infinity. And in between, f is concave down. Okay, is there any information that we have found in all of this work that we have not yet incorporated into our picture?
Local max.
Okay, so Manny, what was the local max? What was the local max? So at x equals 0, the y value is not negative 1, but is 0. Okay, and so when x is equal to 1, the y value of our function is 0. And this is going to be a local max. So let's talk about this interval from negative 1 up to positive 1. Within this interval, we know that this point right here is going to be the top of our hill. And over this interval, our function is concave down the entire time. On the first half of this interval, f is going uphill, and then at the second half going downhill. So I suspect that what this is going to look like is a picture something like this in the middle. Okay? Our function is concave down. The top of the hill occurs at occurs at x equals 0. The value is y equals 0. And this entire curve is concave down. And we have a vertical asymptote at x equals negative 1 and x equals positive 1. So that's our middle part of our function. Okay. Now, other values here here we've got a function that is increasing, so from negative infinity up to